Okay, calculus. Would you make sure you have out your notes from last time, section 1.1 on lines? We're going to continue with these notes. Last time we filled out the front side, and we stopped pretty much on the back side halfway through. Okay, we stopped with 8 and 9. So, if you come down to the bottom, we're going to pick up, we'll do parent graphs in a minute. We're going to pick up on transformations. Okay, transformations, there's a basic thing you've learned in secondary 2 and 3. I like to call it A, H, and K. Y equals A times the quantity x minus H plus K. Where A, if we have a multiplier, actually let me make this a quadratic. That's the first one you learn. If you have a multiplier, A, outside the basic parent function, that multiplier affects the steepness of the graph. If the absolute value of that A is greater than 1, the graph gets steeper. We can also call that a vertical stretch. We have a vertical stretch, and that would make it steeper. If that A is a fraction between 0 and 1, it's a vertical compression, and it gets less steep. Vertical compression gets less steep. And A less than 0, meaning negative, the graph flips. So I hope you remember those. Also, we have inside the function, outside the function, H and K. This is our horizontal shift, vertical shift, in alphabetical order like that. Horizontal shift, vertical shift. If you remember, those are opposite, same, opposite, same. Horizontal shift, vertical shift. I'm just doing the quadratic, but the same placements apply to all the parent functions you've learned. And yeah, we'll go over a bunch of those parent functions on the next page. So, quick transformations. Let's start with the quadratic. The first quadratic we're going to do is number 1, y equals negative 3 times x minus 2 squared plus 4. Y equals negative 3 times x minus 2 squared plus 4. Okay, remember, horizontal shift, vertical shift. Opposite, same. Horizontal shift, vertical shift. Opposite, same. We know quadratic is a parabola. Okay, so we're going to find the vertex of the parabola. Opposite, same. We're going to go right 2, up 4. So right 2, up 1, 2, 3, 4. There is our vertex of the parabola. Now if you look at the A, it is negative, and it is an integer, the absolute value of which is greater than 1. So it's going to be flipped because of the negative, and the 3 makes it steep. And so just for today's purposes, we're just going to draw it down. We're not going to actually find points. Okay, number 2, let's remember what, how to graph the square root function. Our function is y equals square root of x minus 2, the quantity, outside the quantity, plus 3. Okay, horizontal shift, vertical shift. Alphabetical order, H, V. Opposite, same. Opposite, same. So we're going to go right 2, left 3. Or excuse me, down. Right 2, down 3. Let's do that. Up 3. Guys, sorry, it's 5 a.m. Right 2, up 3. That's what I want. Okay. Right 2, up 1, 2, 3. There we go. And what's the A value? The A value is a 1, actually, because there's nothing there. So it just has the standard shape of the square root function, which is just an arc to the right. Okay, next function I'll put out here. Y equals square root 4 minus x minus 3. Okay. Now with this one, underneath the radical, you can see that it's not in the standard order that we're used to. So I'm going to change the order. Y equals square root. Changing the order, I'm going to pull a negative out front and put the x first. Negative x, but if I pull a negative out front, it makes this negative 4, because a negative times a negative would be a positive 4. And then outside the radical, minus 3. Okay, so again we have our horizontal shift, vertical shift. Opposite, same. Right 4, down 3. 1, 2, 3, 4, down 1, 2, 3. That's where it starts. However, see this negative on the inside? Our A, by the way, is 1. But the negative on the inside means it is going to flip, but it's going to flip horizontally, which goes this way. So it's a square root function, but to the left. Okay, those should be reviews. Now, even and odd functions, okay, you should remember these. Here's an even function. Even functions such as the quadratic, because we have an x squared. Even functions have the ability to be folded along the y-axis. So I did this on transparent patty paper so you can see. If we fold it along the y-axis, other than my by hand drawing, you can see it should connect with itself. You can see both of those end up in pretty much the same spot. It's just drawn by hand, so there's a little bit of error. But an even function is symmetric about the y-axis. Okay, so let's write that in. An example of an even function. An example of an even function is a quadratic function. A quadratic, like y equals x squared, has a value, a positive value, so say this is positive value x. It has an negative x value of equal height right there. Because with evens, if you plug in, so do this right here, if you plug in a negative x value into all of the x's in the function, you should get out the original function. So if this is our original function, f of x equals x squared, we replace the x's with a negative x, so negative x in parentheses squared, and negative x times a negative x is still a positive x. So that would be a positive x squared. So f of negative x equals positive x squared, which is the same as the original parent function f of x. Okay? So again, even functions are symmetric with respect to the y-axis. I am really hoping these at least sound familiar. This is all review for the first couple of days. But these are things you definitely need to know before we really jump into calculus. Okay, odd functions. Odd function. An odd function looks like this. It has an odd power, x cubed. Well, guess what? With odd functions, if we fold it around the y-axis like before, you can see through the patty paper that the fold comes up here, but the rest of the graph is down here. Because odd functions take two folds, one about the y-axis and the other one down about the x-axis, and you can see that happen. It's going to pair up right here with the curve down. So odd functions take two folds about the y-axis and about the x-axis. So an example of that is is y equals x cubed. Okay, mathematically, the same thing we have to try is plug in negative x, evaluate the function at negative x. But for every positive x, there is a negative x. But if you look here, the negative x value, the height is going to be the opposite. It's going to be the negative version. If we plug in negative x into all values of, oops, I need to squeeze in a negative. Oops. If we plug in a negative x into the function, we get a negative f of x. So if our original function was f of x equals x cubed, and we evaluate the function at negative x, we'll plug in negative x wherever there's an x cubed. Notice the negative is in the parentheses. And negative times a negative is a positive times a negative is a negative. So f of negative x equals a negative x cubed. So that is the opposite of the original function. So the odd function takes two folds. Let me do this in marker. The odd function, again, we have to fold it across the y-axis and then down across the x-axis. Two folds. Okay, so it is symmetric. We call that if it requires two folds. Symmetric with respect to the origin. Two folds means it's symmetric with respect to the origin. Okay? Alright, flip over to that last page in the packet. We're going to, as fast as we can, go through all the parent functions. Okay. Parent functions. Be ready to do this fast, so I want to get to the juicy stuff that it's more than parent functions, quicker. Okay, so constant. If we're equal to a constant, that is a horizontal line. Just as a reminder, this is independent. The x are the independent variables, the y are the dependent variables. You input the x and you output the y. Okay, what we're going to do is go through the domain and range. Domain I like to write as d sub x, because I like to remember that's against the x-axis. So the domain, we go left forever, right forever, and we call that negative infinity to positive infinity. Now the infinities, remember, we're never going to actually reach, so we use an open parenthesis. The range, I like to do r sub y. Now for the range, I use the y, so I remember that it is vertically along the y-axis. So how far down does this go versus how far up does it go? Well, it only goes as low and as high as that constant a. So this is of height a. So our range is y equals a, because it doesn't ever go below a or above a. Okay, absolute value. Absolute value, I hope you remember, is a v-graph. A v-graph. Okay, domain d sub x, range r sub y. Absolute value goes left, 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 left forever, right, 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 right forever. It also goes, so let's put that negative infinity, positive infinity. The range, it goes down, 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 but then it stops at the origin. Well, this one's at the origin, but the parent function that's unshifted stops at 0, and it actually has a point there, so remember that is a bracket. And it goes up, 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 up forever to infinity. So there's a difference between brackets and parentheses. Make sure you know the difference. Okay, next, quadratic. Quadratics are not a V shape. Make sure you can tell the difference between a V and a parabola that looks like a U. Okay, domain d sub x, r sub y. Domain. The domain goes left, left, left forever. Right, 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 right forever. So that's negative infinity to positive infinity. They won't all be like that, so just keep that in mind. The range, again, goes down, 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 but then it stops at the origin. It never dips down lower than the origin as the unshifted parent function. So we have a bracket, and make sure that's actually a parenthesis, a bracket at 0, and goes up, 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 up forever to infinity. Now, quadratic is also what we call a power rule that is even, a power function that is even. So all powers functions that are even have a basic parabola shape. They might have some squiggles in the middle, but essentially they are a U shape overall. So d sub x, r sub y, the domain still negative infinity, positive infinity, and the range can vary a little bit just depending what the actual exponent or power is, but if we're just looking at a regular parabola x squared, it would be the same, 0 to infinity. Square root function. Okay, square root function starts at the origin and goes to the right, like that. Okay, and d sub x, r sub y. Square root function. Now we finally got something different. Yes. So the square root function doesn't go to the left forever. It goes to the left and stops. The furthest left point is at 0, so that's a closed bracket at 0. Then it goes to the right forever. The range, it goes down until 0, and then it goes up little by little forever. So bracket 0, comma, infinity. I think I'll hold off on logarithmic for just a second. Okay, let's jump over to the identity. Identity function is just equal to constant, which means it's linear. Linear. Okay, d sub x, r sub y. Linear goes left forever, right forever, down forever, up forever. So those are all infinities. Okay, reciprocal function. Reciprocal functions look like this. Remember, you can't divide by 0, so we're not ever going to touch the x-axis, and the y-axis is also an asymptote, vertical asymptote. So d sub x. Now this one is like a handful you'll see on your homework, so make sure you pay attention. This one does go left forever and right forever, but it misses, let's use a color here, it misses the y-axis. So it skips 0 and never touches 0. So we write that as this, negative infinity to 0 with a parenthesis since it doesn't actually touch 0. Then we do union, which means and, or the intersection, parentheses, picking back up as close to 0 as possible, comma, positive infinity. So this is showing we touch everything except for 0 because there's not a bracket at 0. We do a parenthesis at 0. Same thing with the range, because it goes down, down, down forever, up, up, up forever, but we never cross the x-axis or touch the x-axis. So negative infinity to 0, parenthesis, that's an open parenthesis, 0 to infinity. So, and make sure you know this union symbol. Cubic. Cubic function we've mentioned earlier looks like that. It goes down forever, up forever, left forever, right forever. Okay, again, another power where it's odd. Cubic is an example of that. And you can have squiggles here in the middle with cubic, but you can still see it goes down forever, up. Everything's to infinity. So both domain and range is negative infinity to positive infinity. Exponential. I wanted to do this one before logarithmic. Exponential. Okay, so if we had like f of 0 equals a to the 0 power, anything to 0 power is 1. So no matter what we plugged in, we're going to cross the y-axis at 1. Okay, so the exponential, this is a growth, grows up, 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 and that crosses at that point 0, 1. That's important to see how logarithmic graph looks like. So we go left forever, right forever. D sub x, negative infinity, ooh, that's a weird infinity. positive infinity, and we go down, 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 we get super close to the horizontal x-axis, but we're not going to cross it, so that is an open parenthesis, comma, we go up forever. So this is not a bracket, it's open. Okay, the reason I did this one first is because exponential and logarithmics are inverses. This is the inverse of exponential. An inverse means that the x's and y's switch places. So if this crosses at 0, 1, the flip-flop of that would be 1, 0. So the logarithmic crosses here at 1, 0. And instead of crossing the y-axis going up, it crosses the x-axis going up. So x and y switch places on inverses. So the domain and range, guess what? Switches places. It's the exact same thing except for flip-flop. Domain is 0 to infinity with a parenthesis. R sub y is negative infinity to positive infinity. Okay, the greatest integer function. This is a fun one. Okay, sometimes we see this as like L's. Sometimes we see this as like this double bracket thingy. Just be aware that there's different ways to write that. And the greatest integer basically says take any real number x and it will output the greatest integer less than or equal to x. So, quick examples. Let's get a couple things here. 1, 2, 3. If, say, we want to input f of 2, what is the greatest integer less than or equal to 2? Well, that would be 2 itself. So, if we input 2, we're going to get 2. But let's say we input 2.5. We're going to get less than or equal to 2.5 is still 2. But if we input f of 3, the greatest integer less than or equal to 3 is 3. So what's going to happen is we're going to have these horizontal steps with, on the left-hand side is a filled-in circle, on the right-hand side is an open circle, because everything from here all the way over to 3 is going to be of the same, or all the way over to 2 is going to be of the same level, but once we get to that next integer, it jumps up a step. So this is like a step function. Filled in on the left, it's very important you show the difference between filled in and open. Make sure it's very clear if it's filled in or open. I didn't leave any place to write the domain and range. Let's put it right here. The d sub x for the function I've written, it stops at -2, and there is a point actually all the way at 3. But if I didn't do that, yeah, well, -2 to 3. Just be careful. Sometimes you leave it without that last beginning of the step, and it would be an open interval. So just make sure you're aware of what the last point is, if it's open or closed. R sub y, this goes, there are points down at -2 all the way up to +3. close brackets. Okay, sine functions. Whew. Sine function, just as a reminder, sine starts at the origin and looks like this. Height of 1, -1. Oops, I didn't do a very good job getting all the way down to -1. That's a little better. Okay, here is 2 pi. Here is pi. Okay, domain goes on forever, left and right, -infinity to +infinity. The parent function for the range goes down to -1, up to +1. Cosine. Okay, cosine is starts at the maximum and ends at the maximum. That's one wave. And so 2 pi would be over here, and 1 pi would be right here at the minimum. Okay, so the domain d sub x is -infinity to +infinity. The range is the same, -1, +1. Tangent, it looks different. It looks more like the cubic function, but it's a repeated cubic function. And we have these vertical asymptotes here at pi halves. And then another vertical asymptote at 3 pi halves. It keeps repeating, etc. Okay, so this one is really interesting. Okay, the domain, because of all these vertical asymptotes, we have, and it goes on forever to the left, we have, I'm going to start with where the picture starts. We have points that are approaching to the left, negative pi halves, but it doesn't actually touch pi halves, so hence the parenthesis, comma, it goes to positive pi halves, but doesn't actually touch pi halves, so we have a parenthesis, but then remember that union symbol? Union, it's going to get close again to pi halves, went down, 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 but doesn't touch pi halves, comma, goes up to the right to 3 pi halves, but doesn't touch pi halves, and I mean this can continue on, dot, 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 with each of the intervals, with all these unions in between. So the range is kind of funny, or the domain is kind of funny to write. The range is nice. I'm going to put the range up here. Is -infinity to +infinity. Another way to write the domain of x is the set of all x's such that x doesn't equal pi halves or any additional pi halves plus some value k plus k of pi. So k could be 0, dot, 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 because it goes on forever, 1, 0, 1, dot, dot, dot. Anyway, that you don't run into too much. Also know the reciprocal functions, secant, cosecant, and cotangent. Make sure you know those. Okay, because hint, hint, hint on your homework, you have to know those. Okay, if you will pull out, please, the new thing of notes. We're going to go through these as fast as possible. So why don't you guys take a short break and then come back ready to go with section 1.2.